Hello, I'm Julian from the vulnerability research team, and in this presentation I would like to talk about SourceWarp, which is a scalable SCM-driven testing and benchmarking approach to support data-driven and agile decision-making for CI/CD tools and DevOps platforms. This work is joint work from the vulnerability research team at GitLab. And I would like to start with a little bit of background for some of the terms that I'm using throughout this presentation. So first, when I'm referring to Agile, I'm basically referring to the software development philosophy, design philosophy, which is all about shortened design phase of software, iterate quickly, and establish feedback cycles with users and customers, and to integrate this feedback, incorporate this back into the loop as quickly as possible. So to iterate quickly, essentially. Then we also have development, security, and operations like DevSecOps, which essentially builds on the Agile philosophy, but the focus is more on the technical practice within cross-functional teams. But this iteration aspect is also very important for DevSecOps, incorporate feedback quickly and iterate on it. And then we have continuous integration and continuous delivery, CI/CD, which is where the focus is more on the tooling. So it's in the sense the tooling that enables DevSecOps and provide automation around software, which is usually managed through source code management systems, where SCM is the acronym that we are using. And then data-driven decision-making is the process of basically digesting, taking the feedback from users, customers, and then incorporating it to make decisions what the next step would be to incorporate it back into the product. However, when in the context of this presentation, when I'm using the term data-driven decision-making, I'm mostly referring to the process of validating a new feature idea, like taking a proof of concept, for example, and then assessing it, validating it, to basically come to a decision whether or not it should be integrated into the product. Okay, so what was the motivation for building SourceWarp? So I'd like to start with a bird's eye view of a DevSecOps platform. So it's a very schematic view of our platform. So usually we have projects, and these projects, they can have source code management repositories. In our context, it's usually Git repositories, and then developers, they apply changes, they push changes to these repositories, and then we are spinning up jobs. We're running CI/CD tools. These are basically, in our case, mostly Dockerized tools that are spun up, but this can be also tools that are integrated into the platform natively. And these jobs, they're running on the software, so they take the code that's hosted or that's stored in this SCM repository, and then they run on this code and then produce report artifacts, which are then digested by a backend service and then stored in the backend database. For example, you can have a static analysis tool that's searching for security vulnerabilities, and then you would have a CI/CD tool that's running in the context of a job and then producing a vulnerability report that's then digested by the backend database and by the backend service and stored in the database as a sort of historical record. And then we also offer like a variety of different features in a DevSecOps platform. Usually you have like vulnerability management feature, dependency management, license compliance, and many more different features that provide like sort of different views on top of the DevSecOps platform for different personas, so that you can also interact with the data that's actually stored in the backend database. And then there's usually also like an endpoint, an API that people can communicate with to automate some of these tasks. So basically what I wanted to show with this picture is that DevSecOps platforms are heterogeneous. So you have like a combination of different components, and the DevSecOps platform holds all of that together and orchestrates the execution among these different components. So if you're now integrating a proof of concept, so if you have a proof of concept idea, you implemented the tool and you would like to integrate it into the DevSecOps platform, then if this POC is not robust or contains bugs, it can have negative chain effects. So it can impact the whole platform in the worst case. A feature, before its impact can be measured, has to be shipped basically. So we have like a chicken or egg problem. So if you like in an agile context, we want to iterate quickly. How can we somehow evaluate a feature without having to deploy it first, so that we can reduce the risk on the stability on the DevSecOps platform? What we could do potentially is we could reduce velocity, but this is not really an option in an agile setting. Or we could use best practices or common testing strategies like feature flags, A/B testing, canary testing, and we actually use all of that. But the problem is that these techniques, they are not really designed to provide preliminary insights before deployment. They all sort of require to at least partially deploy a feature before you can actually assess it. And another drawback is that especially A/B testing and canary testing are not deeply integrated with source code management systems. And if you like in evaluating CI/CD tools or DevOps platforms, then they're all like centered around the source code management system. And so if your testing technique is actually able to use the source code management system as a source for testing, for source for sourcing test data, test input data, that's actually an advantage. So that was the reason why we came up with the SourceWarp approach. SourceWarp is an SCM-driven testing and benchmarking approach. You can run an experiment on a DevSecOps platform or a CI/CD tool without having to deploy the feature to staging or production. And then you can collect metrics, and you can use these metrics for the purpose of data-driven decision making. You can also rerun experiments while you're actually building out a feature. So this is one of the advantages of not having to deploy, is you can use SourceWarp to get some preliminary insights while you're building out a feature, and then also use that to actually guide your feature development. Okay, let's talk a little bit about the general approach. So this is the overview of the SourceWarp approach. Everything starts with the source code management system. That's like the input data source, so to say, from which we are sourcing the test data. Then we have a record step. This is the step where we actually cherry picking the commits we're interested in, and we're storing them in a record store. Then this record store is used by the patch sequence generator to generate a patch sequence, which is then used in the monitor step here to replay the patches on the target system. So this is like the SUT or system under test, and this target system has its own source code management system, and this is basically derived from the source SCM. So we are kind of creating a copy of the source SCM that goes up to the point where we are replaying where the first patch starts, essentially, that we'd like to replay. And then what happens is that when we're replaying all of these patches on the target SCM, jobs are spun up on the target system, like CI/CD tools are executed, and we can use, in the monitor step, we can run an evaluation script to actually look at some of the results that are produced when replaying, after replaying or while replaying the patches. And then the results are stored at a central place and then are available in the results and metrics report that's produced by SourceWarp. Okay, let's dive into these different steps. So first we look into the record step, and record is all about cherry picking relevant commits. What are the commits that we want to replay on the target system to evaluate our newly developed proof of concept or feature? And first we're looking at the source code repository as an ordered set of commits, essentially. So H in this case is the history, and commits, this is like an ordered set of commits, and they are ordered based on the timestamp. Then we have like two ways how we could impact what commits we want to look into. And the first one is the time interval. So we can tell SourceWarp what are the commits, what's the time interval that we are interested in for extracting the commits. And for that, we're specifying tmin and tmax. And then we would generate a slice. In this case, it's S prime. And this slice contains all the commits that are lying in between T, like we're between tmin and tmax. The second way how we can impact what the commits are that we would like to cherry pick is we can specify an allow list. This allow list can be a set of files. The set of files we would like to consider or be considered by SourceWarp for data extraction. And this is very useful if you have some sort of expert knowledge about the feature you'd like to evaluate, then you can maybe already provide some data about the files you would like to look into. And then you can specify this and provide this in form of an allow list. So then we have our slice, S in this case, and we store this in the record store. And this record store is then used by the patch sequence generator. And the patch sequence generator takes or generates a patch sequence. That's the sequence we are going to replay on the target system. So we're starting with the slice. That's stored in our record store, and then the patch sequence generator generates a set. PS is a patch sequence for us. We only have to provide a so-called patch sequence number. That's the n that you see here, and this n basically tells SourceWarp what is the number of commits that we would like to group together. The advantage of grouping commits together is that we can reduce replay time, because we basically have to spin up less jobs on the system under test, and this is basically like a parameter that helps you to tweak the replay time. And in this example here, you can see we have S with 6 commits, and we specify a patch sequence number of 2, so that we generate this set PS, where we are basically creating pairs of commits. And this here, if you would like compare the replay time between S and PS, then PS would ideally be 2 times faster in comparison. Okay, so now we have the patch sequence, and this patch sequence can then be replayed on the target system. So this is what the replay step does. It basically takes the patches and then replays them on, applies them basically to the target SCM. Then the target system and the target system on the test spins up CI/CD jobs, and we run our evaluation scripts here automatically. So SourceWarp is running them after the application of a single patch. So whenever we apply a patch, we run the evaluation script to collect data we're interested in. And then this data is stored in the results and metrics report that's produced as an output of SourceWarp. Okay, so now let's look into the evaluation. So we did an industrial case study with vulnerability tracking at GitLab. And vulnerability tracking was a problem that we were facing a while back, because at GitLab we are integrating several static analysis tools, and these static analysis tools, they produce security reports, and these security reports are then digested by the backend service and stored in the backend database. But the problem is that there may be some duplicates or some overlap between these different tools. So you may have a problem of double reporting where you have the same vulnerability reported multiple times. So you have to figure out a way how you can dedupe the findings in an efficient way. The second issue is code volatility, because usually code is changing all the time. Developers apply changes all the time, which basically means that a vulnerability that has been detected yesterday can move its location to a different source file or a different place in the code base today. And we have to figure out a way how we can match the finding from today with the one that has been detected yesterday. And this is the code volatility problem. And to solve these two issues, these two challenges, we have implemented a new vulnerability tracking approach. Initially as a proof of concept, and we wanted to reduce the negative effect of double reporting as well as code volatility. And before we actually were able to integrate this feature, we needed evidence about the performance of the feature before deploying it. And that was the reason why SourceWarp actually came in handy, because we could use it to gain some evidence that the idea we have, the proof of concept implementation, does actually work before thinking about integrating it into the product. Because a static analysis is used by many customers, and if there's like a bug or an issue in the implementation, it would impact many people. So it was good to have some preliminary evidence. So in terms of evaluation setup, we basically already had, due to the work on the vulnerability tracking feature itself, we already had basically 2 target systems in place. So we were looking into a Ruby SaaS tool called Brakeman, and luckily these tools are, as we are like dealing with microservices, or that we are often shipping CI/CD tools as microservices in GitLab, we already had them available as Docker images. So Brakeman was already there, and then we created a new version of Brakeman that incorporated our new vulnerability tracking method, and this is called Brakeman plus VT. So to differentiate them, we have Brakeman and Brakeman plus VT, which is the version with the new vulnerability tracking concept and method we implemented at GitLab. And as input for our experiment, we used the GitLab source repository, because it's actually quite good one for testing, because it's fairly big with 3.7 million lines of code, a history of 200k commits at this point in time, and and we were looking at an arbitrary time frame, in this case between October and December 2020. And we also had an allow list that we could specify, because we historically knew which files included vulnerabilities or contained vulnerabilities, which was a set of 60 files that we could include from this period, from this time frame. So and the evaluation worked in such a way that we actually used SourceWarp. We on these 2 target systems, Brakeman and Brakeman with vulnerability tracking, and we replayed the same slice of the Git history from GitLab, and then we just collected metrics about the deduplication performance of both cases, the old version of Brakeman and the new one with vulnerability tracking. And what we wanted to see is that with the new vulnerability tracking method, we actually reduced the number of duplicates, or the overall number of findings. And this indicates if we can reduce the number of findings, and this indicates what the duplication performance of vulnerability tracking is. As part of this research experiment, we wanted to evaluate 2 research questions. The first one was, is SourceWarp effective in supporting data-driven decision making? And the second one is, what's the impact of the allow list and the patch sampling number? So in terms of time, this is the table that shows the execution time for SourceWarp in both cases, running on Brakeman and Brakeman with vulnerability tracking. You can see that they're almost on par. It's almost the same execution time. Actually, Brakeman with vulnerability tracking was a bit faster, and the reason is that the overhead of the vulnerability tracking method is kind of shadowed by the Docker spin-up time, because in this case we actually used the Brakeman and Brakeman plus VT Docker containers that we spun up, and the spin-up time is fluctuating a little bit, and sometimes faster, sometimes a bit slower, and the overhead of VT is completely shadowed by that. And what we can basically say or tell from the data is that the overhead of vulnerability tracking is can be ignored, so it's negligible. It doesn't play a big role, which was a good thing for our experiment. So overall, the overall execution time is almost the same, and there's no big difference. We observed no big overhead caused by vulnerability tracking in terms of execution time. And then about the errors and fingerprints. So we also wanted to know if there are crashes, if you observe crashes or errors. We didn't observe any, so that means that vulnerability tracking didn't include any errors, didn't cause any bugs. And then the next data point we were interested in is the number of unique fingerprints after applying a patch. So a vulnerability is identified by a fingerprint, and the lower the number of unique fingerprints, the better the deduplication performance. And as you can see here, the vulnerability tracking already starts out with 11 less reported vulnerabilities, so it dedupes some of the findings that the original Brakeman analyzer did find or did detect, and this increases over time. So if you're looking at the delta apps, that's the absolute number, the absolute difference between the number of fingerprints for Brakeman and Brakeman plus vulnerability tracking. You can see that this increases over time. So after applying the 13th patch, we already had like 40 vulnerabilities we could actually deduplicate using a new method, which is a 30% improvement, which essentially you can read this as vulnerability tracking reduces the manual effort of filtering duplicates by 30%. And it's increasing over time. So you can see that it's the percentages are increasing as we move forward. So in terms for the first research question, is SourceWarp effective in supporting data-driven decision making? We can say yes. So the experiment that you just saw was completely automated and done in a reproducible way. And we used it to measure overhead, cost savings, and robustness in an automated manner. And it collected all the data that we required to make an informed decision about the actual product integration of vulnerability tracking. Then research question 2 is about the impact of the allow list and patch sampling number. So the allow list, actually, if you're looking at the if you would have only used the time frame approach, then the slice that we had to replay would have had the size of about 2,700 commits. And if you assume that every single commit replay time is on average like 1 minute, maybe 20 seconds, it would have taken basically 61 hours to replay the slice. And by using the allow list, we could reduce this to the slice size to 131. So that we could actually replay the whole thing within 3 hours, which is already pretty good. So you could run such an experiment while building out the feature within 3 hours. And then the patch sampling is another factor. If you in our case, we decided to go with a patch sampling number of 10, which was good enough. In our case, it provided us enough granularity to make some sort of assessment about the progression of findings over time, and this further reduced the execution time from 3 hours to 18 minutes. So what we can clearly say is that both of them, the allow list and the patch sampling numbers, helped us to reduce the benchmarking and testing time from days to hours, and this enables us to actually run these type of experiments while building out the feature. Okay, so to sum up this presentation, first you want to say that if you want to know a bit more and get some sort of see a tool demo and read a bit more about the SourceWarp approach and background, you can also check out the blog post, which you can find under this URL here. And as a summary, at the beginning we talked about the motivation, about the context, what the reason was why we built it SourceWarp in the first place, and we talked about the architecture of DevSecOps platforms, and that they're heterogeneous systems where it can be risky to integrate new features, and it is good to have some sort of testing approach that enables you to get some preliminary data about a feature before deploying it. Then we talked about the approach, about the different components with like record step, patch sequence generation, and monitor. And then we talked about the industrial case study where we applied SourceWarp for evaluating vulnerability tracking. And then we also talked about the evaluation and about the two research questions, that showed that SourceWarp was effective to support data-driven decision making, and the impact of the allow list and patch sampling number was great to actually make SourceWarp scale to big repositories and make it possible to run it while building out a feature. And yeah, with that, I would like to close, and thank you very much for your attention.